Hello, my name is Maverick Madison, and this is the exam review for IEE 380. And today I'm just going to be covering some practice questions for your guys' upcoming exam. Um, so this exam review will be covering just some certain topics, and I do have some more topics that have been previously covered in a previous exam review that I made last semester, and I'll give you guys the link to that one so that you guys can watch it. So, question one, an engineer is participating in a research project on the title pattern of junk emails. The number of junk emails that arrive in an individual's account every hour follows a Poisson distribution with a mean of 1.8. What is the probability that an individual receives more than 3 junk emails in the next 3 hours? So for this first problem, we're working with a Poisson distribution. Since we're counting the number of emails over a time interval, we can see that the average rate is 1.8 emails per hour, and we're looking at a 3-hour window. So our new mean becomes 1.8 times 3, which gives us a value of 5.4. And we want the probability of getting more than 3 emails. Instead of summing everything above 3, we can just simply do the complement, which is simply 1 minus the probability of getting 3 emails or fewer, as showcased here, 1 minus the Poisson CDF function. The first parameter is just that new mean we calculated, 5.4. And the second parameter is the x value we're measuring, which is simply 3 hours as the time interval. And plugging this into our calculator, this ultimately gives us a final probability of 0.7867, or just above 78%. Moving on to question two. The diameter of bolts manufactured by an engineering company follows a normal distribution with a mean of 12 millimeters and a standard deviation of 0.4 millimeters. Bolts with diameters outside of this range of 11.6 millimeters to 12.4 millimeters are considered defective and must be discarded. What is the probability a randomly selected bolt is defective? So for this question, we are following a normal distribution, and we are given the mean of 12 millimeters, and we're given the standard deviation of 0.4 millimeters. And we're also told that anything outside the interval from 11.6 to 12.4 millimeters is defective. So first, we want to find the probability of a value that is inside of that range and just simply subtract it from 1. Since we're trying to find the probability that a bolt is defective, everything outside of this range is defective. So if we simply subtract that range from 1, we'll get that whole genre of defective bolts. And so in order to find all those non-defective bolts inside of that range, we simply plug it into our normal CDF function using the first parameter being the lower bound being 11.6, the upper bound being 12.4. We have our mean and our standard deviation, 12 and 0.4. And we plug that into that calculator function, subtract it from 1. We get a corresponding probability of 0.3173, or just above 31% for a defective bolt. Moving on to question 3. At an Amazon fulfillment center, packages are sorted randomly onto one of 5 conveyor belts for delivery preparation. Assume the selection of a conveyor belt follows a discrete uniform distribution. What is the probability a package is assigned to one of the first 3 conveyor belts? So here we're just following simple discrete uniform distribution. And so we have 5 conveyor belts, and each conveyor belt has a probability of 1 in 5, or basically 0.2. And we want to find the probability of landing on one of the first 3 belts, so we simply just add those probabilities. Each of the conveyor belts has a probability of 0.2, so we just add 0.2 plus 0.2 plus 0.2, which is just 3 over 5, or just 0.6. So that is our final answer, 0.6, being the probability that a package is assigned to one of the first 3 conveyor belts. Moving on to question 4. A sensor in a factory measures the temperature of a machine component, where the temperature is modeled as a continuous random variable uniformly distributed between 25 degrees Celsius and 75 degrees Celsius. What is the probability the temperature is exactly 55 degrees Celsius? And so the key idea here is that for any continuous random variable, just by definition, the probability of taking on exactly one value is 0. So, since that's exactly what this question is asking, the probability that the temperature is exactly 55 degrees is simply zero, according to the definition of continuous random variables. Moving on to question 5, customers who are registered on a corporate website are summarized by the type of shipping contract they use and the number of orders in the previous month. The number of customers in each category is shown in the following table. And so in this table, we have 2 columns and 3 rows, an express column, a standard column, and for the rows, we have no orders, 1 order, more than 1 order. And here we have our corresponding values. What is the probability that a selected customer did not order in the previous month, given that all of last month's orders used express shipping? And so this question is a conditional probability problem where we're given a table and we're asked for the probability that a customer had no orders, given the fact that we're only looking at express shipping from last month's orders. So in this table, we want to focus on just that express column. So we could ignore the standard column. And this express column, if we sum up all the values in that column, we have 143 entries or so. So out of the 143 entries in this column, 32 of them were no orders. So given the fact that we have the express column, the probability that the selected customer did not order anything is simply 32 over the entire column, which is 143 entries. And so that is our probability. We just divide 32 over 143, and that gives us 0.2238, or just above 22% probability that a selected customer did not order in the previous month, given the fact that all of last month's orders used express shipping. Moving on to question 6, a company monitors the strength of its manufactured cables. The strength of these cables is normally distributed with a mean of 40 and a standard deviation of 4. What is the probability that a randomly selected cable has a strength greater than 47? And so this is simply another normal distribution problem. We're given the mean of 40, standard deviation of 4, and we want to find the probability that the strength is greater than 47. So again, we can just use a complement here. Since we're asking for strength greater than 47, that's also the same as just taking everything that's less than or equal to 47 and subtracting it from 1. And so in the normal CDF function, our lower bound is simply negative infinity, and our upper bound is 47. And then we just pass in our mean and standard deviation parameters, plug it into that normal CDF function, subtract it from 1, and that gives us a probability of 0.04006, or just slightly above 4%, which is actually pretty small. Moving on to question 7, a long traffic light on your morning commute is green 10% of the time that you approach it. Assume that each morning represents an independent trial. Over 15 mornings, what is the probability that the light is green on exactly 3 days? And so this problem is similar to a problem that I did in the tutored concept videos, which in that case, it follows a binomial distribution. In this problem, we're given a fixed number of trials, being 15 mornings. We're given an assumption that each morning represents an independent trial, and as well as a constant probability. The light is green 10% of the time. And so here we simply have all the parameters we need to plug into the binom PDF function, since we're looking for an exact value, not just a range of values. So here we would use the binom PDF function instead of the CDF function on exactly 3 days. The first parameter being the number of trials, 15 mornings. The second parameter being the probability that the light is green, which is 10%, and the corresponding x value, which we're measuring exactly, which is 3. And so plugging that into the calculator function, we get a probability of 0.1285, or just above 12%, that the probability of the light being green on exactly 3 days. Moving on to question 8. A power plant turbine operates with a temperature range of 200 degrees Celsius to 400 degrees Celsius during normal conditions. The temperature is assumed to follow a normal distribution over this range. What is the probability the turbine temperature is between 215 degrees Celsius and 360 degrees Celsius? And so for this problem, we're working with a continuous uniform distribution between 200 and 400 degrees Celsius. And so for a uniform distribution, probability is just the length of the interval over the total range. And it's showcased in this formula here of the probability that C is less than or equal to X, which is also less than or equal to D. And this is basically the range that we're dealing with. We're dealing with 200 to 400 degrees Celsius. We're looking for the probability that the turbine temperature is between 215 and 360. So those are just simply our C and D variables. And our A and B variables are just 200 and 400, as that is the operation for the temperature range. And so with this, we can just compute it. We have our D being 360, our C being 215, B being 400, A being 200. We plug it into this function here of D minus C over B minus A. And that gives us 360 minus 215 divided by 400 minus 200, which is simply 145 over 200, which we end up getting here as well, or just a probability of 0.725, or just above 72%, that the turbine temperature is between that range of 215 to 360 degrees Celsius. For question 9, the following table summarizes 215 endothermic reactions involving sodium bicarbonate. And here we're given a table with 2 columns, 3 rows, a column for below target, column for above target, and rows for the final temperature conditions in degrees Kelvin, 266, 271, 274. And let's denote the variable A as the event that a reaction's final temperature is 271 degrees Kelvin or more. And let's let B denote the event that the heat absorbed is above the target. So we want to determine the union of both those events. And by definition, we have a formula for this union. It's basically just the probability of event A plus the probability of event B minus the intersection of both those events. And we're given that event A is the temperatures of 271 degrees Kelvin or higher. So basically, we would just sum up all of these columns, being that 271 or higher is including 271 and 274. So we add 46 plus 48 plus 14 plus 61, and that gives us a total of 169. And there are a total of 215 endothermic reactions, so that would be all over 215. The probability for event B is just all the values above the target. So it would simply be 31 plus 14 plus 61, which gives us a value of 106, and we still divide that over the 215 endothermic reactions. And so now we have the probability of event A, probability of event B. So we know that in this table, the probability of event A covers this range of the table, 46, 14, 48, 61, and the probability of event B covers this entire above target column. And so we do see an intersection point between those two, and these are highlighted in yellow here. And so that is the overlap there. That is our intersection. So we just add 14 and 61, giving us 75, and all over 215 endothermic reactions. So that is our intersection point. So simply, we would add both the probability of event A and event B, and we would subtract that intersection point. And ultimately, we get a final answer of 200 over 215, a probability of 0.9302, which is just the probability of A union B. Moving on to question 10, which statement is true about continuous random variables? A, the PDF gives the probability of X at a specific value. B, the CDF always decreases as X increases. C, the probability that X is equal to X is equal to 0 for all values of X. D, probability that X is equal to X is greater than 0 for some values of X. And so this one's just another definition problem. For continuous random variables, the correct statement is the probability of a variable taking on an exact value is 0. So that would just simply be C, highlighted in yellow. Moving on to the last question, question 11. The time between failures of a particular machine component follows an exponential distribution with an average time between failures of 4,000 hours. What is the probability a component fails within the first 1,000 hours of operation? And so for this problem, we're given the fact that it is an exponential distribution problem with an average of 4,000 hours. And so here we can use the cumulative distribution function for exponential distributions. And this is defined as 1 minus e to the negative x over the mean. And we're finding that the probability that the component fails is within 1,000 hours. So we would plug in 1,000 for this measurable value for little x. And our given mean is 4,000. So we have everything we need to plug into this exponential distribution cumulative function. And that gives us 1 minus e to the negative 1,000 over 4,000. Or that simply reduces down to 0.2212, or just above 22% probability that a component fails within the first 1,000 hours of operation. And so that has been this brief exam review video for the big chunk of concepts being covered in your guys' final exam. Once again, I did make a video last semester which covers the other half, which focuses more on the hypothesis tests and the inference problems. So I would highly recommend giving those a watch as well to review for you guys' final. But other than that, I thank you guys for watching. And if you guys have any questions, feel free to reach out to me through email or through the course Discord. Thank you.